Now it is time for our first keynote speaker, who truly needs no introduction. There's someone in the front row here who tried to wrestle me out of the way to get close to Dr. Geoffrey Hinton to say how much he means to him. So I really think he needs no introduction, but I shall give him one. Dr. Geoffrey Hinton is Chief Scientific Advisor of Vector Institute, as well as one of its co-founders. Dr. Hinton designs machine learning algorithms. He aims to discover a learning procedure that is efficient at finding complex structure in large, high-dimensional data sets, and to show that this is how the brain learns to see. He is one of the researchers that introduced the backpropagation algorithm and the first to use backpropagation for learning word embeddings. His other contributions to neural network research are many, including the Boltzmann's machines, distributed representations, variational learning, and deep belief nets, to name a few. Geoffrey's research group in Toronto made major breakthroughs in deep learning that have truly revolutionized speech recognition and object classification. A little bit about Dr. Hinton's history. He is a BA in experimental psychology from Cambridge and completed his PhD in artificial intelligence in 1978 from Edinburgh. He did postdoctoral work at Sussex University and at the University of California, San Diego, and spent 5 years at Carnegie Mellon, and then came north to Canada, where he became a fellow of the Canadian Institute for Advanced Research and moved to the Department of Computer Science at the University of Toronto. He crossed the pond for 3 years, where he set up the Gatsby Computational Neuroscience Unit at University College London, and then returned back to Canada. From 2004 to 2013, he was the director of a program on neural computation and adaptive perception, funded by CFAR. In 2013, Google acquired Hinton's neural network startup, DNN Research, which he developed out of his research at the university. He is Vice President and Engineering Fellow at Google. He is a Fellow of the Royal Society of Canada, and the Association for the Advancement of Artificial Intelligence. Dr. Hinton has inspired and supported many, many researchers throughout his career who have also gone on to do incredible things with their careers. He has received many awards and accolades for his groundbreaking work, and I just wanted to highlight a couple of them. In 2010, Dr. Hinton received Canada's top award in science and engineering, the Ensert Hertzberg Gold Medal. In 2017, he was given the BBVA Frontiers of Knowledge Award in recognition of his world-class research. In 2018, he won the Turing Award together with Jan LeCun and Yoshua Bengio. And in 2019, he received the Honda Prize, which is awarded to an interdisciplinary researcher who is addressing global challenges and contributing to the creation of a truly humane civilization. I could go on, but I won't. So please do join me in welcoming Dr. Geoffrey Hinton.
When people get old, like me, they sometimes have the idea that what they're going to do is upload their mind to a computer. Today I'm going to tell you why that idea is ridiculous and will never work. So, there they are. So, in conventional computing, there's a separation between hardware and software, and that's very important. It's probably the most fundamental principle of computer science, that the hardware should be separate from the software. We've got a problem here that I normally read my slides so I know what I'm going to say next, and I can't read them. If I go over here, I'll be okay. Yeah, okay. The point about that separation is you can have knowledge in a program or in a set of weights, and you can run the same knowledge on a different chip or a different computer. So when the hardware dies, the knowledge doesn't die. But you achieve that at a great cost. That's a wonderful thing to have. It means you can make 1 million copies of the same program and send them to 1 million cell phones. But to do that, the computer has to act in a reliable way. So we have to run transistors at high power, so they're nice and digital. and we need to fabricate the hardware so it does what you expect it to do, and so another copy of the hardware will do exactly the same thing. Now, if we abandon that immortality, in literature what you get back is love if you abandon immortality, but here what we're going to get back is something even more important, which is low energy. We can use very low power analog hardware that's unreliable, and we don't need to know the precise connectivity of the hardware. So the idea is that the whole of the field of computer science relied on separation of hardware and software, and people are now busy saying, if I have a big set of weights, how do I explain how it really works? I want to go in exactly the opposite direction. Sort of based on the brain, I want to say the knowledge and the hardware are intimately entangled and we'll never separate them. For this to work, there has to be a learning procedure that operates in a particular piece of hardware and makes use of all the weird analog properties of that particular piece of hardware. That's what I call a mortal computer. So it has the advantage that we can use immense parallelism. We can use parallelism at the level of the weights, and so the computing elements don't need to run very fast, which keeps them lower power. Also, we don't need to fabricate these things. Fabrication is getting more and more expensive. You need like $1 billion. Actually, I think that was a few years ago. You need several $1 billion now to make a fabrication plant. Instead of doing that, what we can do is grow these things very cheaply and very unreliably. That's going to involve a lot of nanotechnology. But these are my predictions about something that's coming, maybe not in the next couple of years, but is coming in the next decade or so, and will be a completely different kind of computer that violates a lot of the very basic assumptions you make, that you can separate the knowledge from the hardware. There's two big problems, of course, that are preventing this happening. It seems like a problem that when the piece of hardware dies, everything it's learned dies, because you can't copy the knowledge in a neural net by just copying the weights. If those weights are running in hardware that's very flaky, very specific to that particular instance, and where you don't actually know all the details of the connectivity or the input-output functions of the neurons, if you have things like neurons. We also need a learning algorithm that will allow a mortal computer to make use of its hardware properly. And we don't have one yet. Backpropagation's not the right algorithm. In backpropagation, you have to know exactly how the forward process works in order to backpropagate gradients. And I believe the big bottleneck in having this different kind of computer, these mortal throwaway computers, is that we don't yet have the right learning algorithm. So I'm going to just show you that it's not impossible to get a learning algorithm for things like this. This is some very old ideas, updated slightly recently. A really simple learning procedure is just you make a random vector of changes to the weights, and then you look and see how much that improves things, and you then multiply the vector of random changes by how much it improved things, and you make that be a permanent change to the weights. And everybody knows that'll work. It's unbiased. It's noisy but unbiased. But it's just incredibly slow because it has a lot of variance. Also, you can't use matrix multiplies with that. Matrix multiplies because you need to make different perturbations on every case. Otherwise, you get very high variance. Now, instead of doing that, people about 30 years ago figured out that you could perturb the activities. So you add a random vector of perturbations to the total input to a neuron, and you do the same thing. You say, how much did that random vector improve things? And let's multiply that random vector by how much it improved things, and add that to what we want to happen to the inputs. So then you've got an unbiased estimate of the derivatives with respect to the total inputs to the units, and then you can just go and compute how to change the weights to follow that gradient. That's a much better algorithm. It's got much lower variance. The things that you're adding noise to are the neurons, not the weights, so there's thousands of times less of them. The question is, and it works for small things like MNIST, but will it scale up? So one way to make it scale up to much bigger networks is instead of trying to find an algorithm that scales to more parameters, have an algorithm that works quite well if you don't have that many parameters, and just scale up the number of modules you have that have that many parameters. And the human cortex is a bit like that. It's got millions of these relatively small modules. To do that, you need to have local objective functions for these modules. And that's how you can make these not very efficient learning algorithms scale up to very big systems. But where do these local objective functions come from? Well, one possibility is unsupervised contrastive learning. So there's a method suggested in the 90s by Sue Becker and I, but we didn't get a very good version of it, where you just try and make two sources of information agree. So you take two patches from the same image, and you try and make them agree on their representation. The modern version of that uses a contrastive method where you use negative examples, where you take two patches from different images and say they should be different, and two patches from the same image and say they should be the same. And that's how you get, that's your objective function. I've left out all the details of specifying in terms of log probabilities, but most of you know that. You could take that algorithm and have little modules that are trying to make representations from one patch agree with representations of other patches. And you could have each module have a few hidden layers. You could use this kind of activity perturbation algorithm, and then you could have greedily between multiple layers, and that way you can learn representations, and then right at the end you can associate the representations with the right answer. So you just learn a linear model at the end, which doesn't require backprop. So there's a very good researcher, and one of the best that Vector has produced, called Mengyi Ren. He's been messing about with a variant of the activity perturbation method. I don't have time to go into the details, but he's basically shown that it can be made to work. This isn't that convincing evidence, because I think Mengyi could show that anything could be made to work. But he has some results which I don't have time to go into, where you compare using backpropagation in these local modules with using activity perturbation to get your gradient. And the question is, will this work for relatively large problems like ImageNet, as opposed to just small problems like CFAR? And if you look at the first number in the right-hand column, in the kind of nets he was using, which weren't that big, backpropagation using this contrastive learning objective gives you 55% error rate, so you get about half of them right. And if you look at the bottom entry in the right-hand column, this local activity perturbation gives you about 75% error rate, so you get about a quarter of them right. Since there's 1,000 possible answers, that's still not bad. So you can actually make this scale up to things of the size of ImageNet, where you have millions of connections, many millions of connections. But I'll leave it at that, because that's not really what I want to talk about. I just want to show it is possible to get learning algorithms other than backprop that sort of work, and we'll be able to make them work better. In these mortal computers, the other problem is, how do you transfer knowledge? You don't want the mortal computer to just die and lose all the knowledge. And also, how do you transfer knowledge within the computer itself? So vision systems use convolution, or they use transformers that apply the same weights to different patches in the image. And you can't do that in one of these mortal computers, because different patches of the image will be handled by hardware that was grown and was unreliable and is slightly different from the hardware that handles some other patch. So you have to use knowledge distillation. And in knowledge distillation, what you do is you learn stuff in one location, and then if you've got some contrastive kind of objective function, or if you say, I would like what I produce from one location to be predictable from what I produce in other locations by some simple function that I learn, then you can get knowledge between locations by using distillation, by using the context as a teacher for the local thing, and that goes on everywhere, so everything can get taught by distillation. And that's actually better than copying weights across, because that can cope with the fact that your front end, your retina, might have different size receptor fields with different spacing for different modules, but modules can still transfer knowledge to each other by giving each other targets for learning. There's distilling knowledge between mortal computers. So the way distillation works is, once you've trained a computer, it can give you not just what the right answer is, but probabilities of all the wrong answers. And that's much richer information than just the right answer. And that means you can train another computer from those probabilities much better than you can train it just from the raw data. And in a community of mortal computers, what we want to do is get the internal knowledge from one to another. We can't copy weights. The internal knowledge isn't in the form of programs or symbolic expressions that we can copy. It's gunk, a huge bunch of weights tied up with a huge bunch of hardware that works in weird ways that we don't understand. The way to get the knowledge across is to produce extra outputs that are learned just in order to get the knowledge across. And that's what I think one of the main functions